This video we're going to review how to calculate empirical and molecular formulas. It's super important before you look at this tutorial that you know what an empirical and molecular formula is from a vocabulary perspective, or this is going to be really hard to follow. So if you've not done so yet, pause this, go back to the text, read over this section. There's a Tyler DeWitt video that I posted, and he does a super slow walkthrough, kind of explaining what conceptually an empirical and molecular formula are. Having that understanding coming into this mini tutorial will help you immensely, and it'll be worth tremendously that extra 10 minutes that you're putting into making sure you understand that vocabulary piece before just jumping into a problem with a bunch of words you're not going to understand. Before I do an empirical formula example, I wanted just to do one showing you how to calculate percent composition. I do think that the textbook does a really good job walking you through step by step how to do these, but since they do kind of tie well into empirical formulas, I thought it would be good just to maybe go through one of those. I'm going to do one from exercise number 1. This is in the determining empirical and molecular formula section of your textbook under unit 2. And we're given the compound Na2S2O3 and asked to calculate the percent composition of each element that makes it up. So whenever you're doing these percent compositions, you're going to separate out the elements that there are. We have 3 of them. Your next step is you need to determine how many of each atom there are. So we have 2 sodiums, we have 2 sulfurs, and 3 oxygen. Okay, then we are going to multiply by the atomic mass, which you find on the periodic table, that number underneath there. Sulfurs is 32.06 and oxygens is 16. Okay, and then you're going to get those totals. So whenever you're calculating percent composition, pretty straightforward. You're going to find the mass that each element contributes to the compound. You're going to add up all of those 3 masses. So if we add the sodium's mass, the sulfur's total mass, and the oxygen's total mass, you'll get the total mass of the entire compound overall, which is 158.10. And each of those atoms' mass, you're going to divide by the total of the mass of the whole compound. Since a percent composition, in order to put it into percent, we have to multiply by 100. And then you'll be told what to round to on those percentages, but it's typically going to be to the 100th place. And then that's it, okay? So on your percent composition problems, all you're doing is calculating of that mass of that whole compound, what percent does each atom contribute to that? So it's a really kind of straightforward, if you can do formula masses, it's just a version of that. Now, empirical formulas, it's kind of the opposite. Instead of given the compound and asked to figure out what the percent composition is of each element, empirical formulas are kind of the opposite, where you're told the percent composition of each element, and then you're told to generate from the percentages the actual formula. So there's, I think, again, the textbook does a really good job walking you through how to do these. But I have like a little shortcut. Back when I taught high school, one of the students came up with this, and I've used it ever since just to kind of help other students be able to even more simplify this process. So it's kind of a little poem. It's percent to grams, grams to moles, divided by small, multiplied to whole. And those are essentially the steps that you take in order to do an empirical formula problem. I italicize the first and the last because some problems you might not have to do one or both of those steps, depending upon what information you're given. So in the ones that we're going to do today, you'll see some examples of that. All right, so for empirical formula, the one that we're going to do is example 3 out of your textbook in that section. And it asks, what is the empirical formula of a compound if a sample contains 0.130 grams of nitrogen and 0.370 grams of oxygen? So whenever I do these problems, I always start by listing the atoms or elements that are present in the compound, kind of putting them on top of each other. I'm going to run kind of like 2 simultaneous problems as I go through. All right, so looking at my little empirical formula poem, the first step says is to take my percentage and put it into grams, only if needed. Well, if I look at my numbers, they're already in grams, so I won't have to do that step. Okay, so that first step is bypassed. Then I go to the second step, grams to moles. So exactly that's what I'm going to do. I'm going to have my nitrogen, of which I have 0.130 grams. And then I have the 0.370 grams of the oxygen. Okay, and I'm going to convert these grams to moles, which we've done lots of these at this point. So grams to moles, we know we can do in one step. We know the number of moles is 1, and the grams is the atomic mass from the periodic table. If you look up nitrogen, it's 14.01. Okay, I'm going to go ahead and do that for oxygen. Convert it to moles. One always goes with moles. My mass of oxygen is 16. And then I can solve the first part. I will say, super important piece on this part where you're converting grams to moles, do not round your answer using sig figs yet. You want to keep as many decimal places as you can. If you start rounding too soon on these problems, you're going to find yourself in a really tough situation because your numbers aren't going to work out. So in empirical formulas, always keep as many numbers as you can kind of write down that you can fit. So if you divide this, you're going to find that you get a pretty long number. I'm going to write down as many as I can kind of squeeze in there at the moment. I would definitely take it to at least 4 sig figs, preferably 5, whenever you are doing this first mini conversion step. Okay. And if you keep all of them, even better. Okay, so that's my first step, grams to moles. The next says divide by small. So what that means is I compare all of the moles. In this case, there's 2 of them. I pick the smallest number between the 2, and each one gets divided by that number. So in this case, I have 2 of them. This one is the smaller number. So I'm going to go ahead and divide both of those by that smaller number. And whenever I do that, I'm going to get 1 here, obviously. And then whenever I divide this one, I'm going to get 2.5. All right, my next step says multiply till whole. So what that means is if one of these is not a whole number, which is the case here, then you have to find a number to multiply it by, the lowest number you can, in order to get it to a whole number. So this is an instance where I will have to multiply to a whole. I'm going to look at 2.5. What's the lowest number I can multiply 2.5 by in order to give me a whole number? Think about it, it should be 2, right? 2.5 times 2 gives me 5. But what you do to one part of the compound, you have to do to all of it. So even though this is a whole number, you still also have to multiply it by that same 2. So that'll give you this 2 here. So if this are going to be my number of atoms, so my final answer is going to be N. It's going to have its subscript of 2, and O is going to have a subscript of 5. And that would be your answer there. Okay, so that's one example. So I'll get one more. This is example 4 in your text. Again, asking for the empirical formula of a compound, and it gives you the percentages of 3 elements that are present. So we're going to have carbon, hydrogen, and oxygen. Okay, so onto my little poem. It says percent to grams if needed. This one I am given percentages, so I do have to put it in grams. Good news is that's super easy. All you do is just swap out your percentage for a gram. So this is going to be 40.0 grams, 6.71 grams, and 53.28 grams. Okay, and then all of those, once they're put into grams, my second step is taking grams to moles. So we can go ahead, use our molar masses, and convert each of these from grams to moles. And then oxygen is 16. Okay, remember this step, you want to keep as many decimal places as you can squeeze in on your paper whenever you're answering this first step. Okay, so we did percent to grams, grams to moles. Next we divide by small. So I'm going to compare all of these numbers. The smallest one is the 3.33. So all of these are going to get divided by the smallest number. Okay, last step says multiply till whole. That's another only if needed. If you look, all of these are whole numbers, so there's no need to multiply till whole. So if I go ahead, I'm gonna have 1 carbon, 2 hydrogens, and 1 oxygen. And that's going to be your empirical formula for that problem. It's important worth noting, if you get an answer that's like 0.9998, don't count that as a decimal. That's close enough, you can round to 1. Really, the only numbers that you have to worry about putting in as a decimal would be like a 0.5, a 0.3, or a 0.25. All of those you would multiply to get to a whole, but if you have like 1.005, again, that's close enough to just round those ones to the whole number. So hopefully that helps for empirical formulas.